Okay, so thank you very much for the invitation. It's a pleasure to be here. So let me say why talk about this and why I got interested into this. It was around 1 year ago. I saw a talk online by Michael Douglas, sorry, the string theorist. And in this talk, he was using machine learning methods to try and approximate Ricci-flat Kähler metrics, Yau's metrics on Calabi-Yau manifolds, and then using those to try and find closed geodesics using numerical methods. But that's quite hard to do because it might look that they close, but maybe they don't. You don't. So it is a challenging thing to do. And the reason why he is interested in these, I think it's because these are bound states in some supersymmetric nonlinear sigma model, something that appears in theoretical physics, which target such a Calabi-Yau manifold, right? So I started thinking maybe using some methods to approximate such metrics, we can also approximate the geodesics and actually see how many we can actually locate. And so that's what this project is about. And then as I was doing this, I realized that there is actually relations to an open problem in electrostatics that was posed by Maxwell in 1873 and by J.J. Thomson, the guy that discovered the electron, also in the beginning of the 20th century. So that's quite interesting. So I'll start by telling you about this problem in electrostatics, and then I'll circle back to the case resurfaces. Okay, so some problem in electrostatics. I do this just for you to pay some attention to the problem because it's quite interesting. So I'm going to start with the electric potential generated by unit point charges at some points in R3. So this is defined up to a constant. I'll call the constant M. So that's basically the Coulomb potential generated by unit electric charges at the points P1 up to Pn. So that's the electric potential generated by unit electric charges at P1 up to Pn, some points in R3. So if this is the electric potential, and the electric field is the gradient of the electric potential. That's the electric field. And the point P in R3 is called electrostatic if the electric field there vanishes. Is an electrostatic point that's basically the points where you can put a test charge and it doesn't move anywhere. It stays. It stays there. So said in other words, these are the critical points of the electric potential. Okay, so let's see some examples. Of course, if I have just one charge, there is no electrostatic point. But let's say I have two charges. So the number of electric charges is 2. So I have one here, another one there. And of course, there is an electrostatic point right at the middle. Let's now suppose I have 3 electric charges that I arrange in a line. One here, one there, and another one there. And they equidistantly, let's suppose that. So in this case, the electric potential goes to infinity there, goes to infinity there, goes to infinity there. And it has 2 minima here when restricted to this line. These are not global minima because they are saddle points, because phi is actually an harmonic function away from the points. So it can have no local minima or local maxima. But there are some electrostatic points, just to write this. But now they are not exactly in the middle. They are a bit closer to this point because there are 2 electric charges on that side and only one on this and another one there. Somewhere in between there are. So we have 2 here, the number of electrostatic points was equal to 1. Here, the number of electrostatic points is equal to 2. And now let's suppose that instead of arranging the 3 points in a line, I put them at the vertices of an equilateral triangle. Like that. So now, how many electrostatic points are there? Does anyone want to guess? How many are there if I put them like that? No, they are isolated, yeah. So, so you say 3, 4. That's 4 is the correct answer, but there are at least 3, yes. So one of them is exactly at the barycenter, right? Everyone agrees with that one, right? And then there are 3 more. I'll just draw these lines. These give you reflection symmetries of the triangle, and they are somewhere here. Okay, so everyone understands the blue one, I hope. Is that okay? Let me try to end wavily explain the other ones. So the point is that if you move a little bit away from the center, let's go along this line, okay? Everything is invariant by reflection along this line. So along this line, the electric field needs to point along that line, right? So if you move a little bit away, further down, you will see that the electric field actually points down. Because just imagine there are 2 charges here, only 1 there, so maybe you can believe me on that. But if you move all the way to the edge of this triangle over here, then there is no electric charge on this half plane, and there is one on this one, right? So it needs to point up. So somewhere in the middle, there needs to be a 0. Okay, so that explains that one and also this one. Okay. So there are actually 4 electrostatic points, and I've drawn them with different colors. Maybe I'll come back to these later. Let's just do one more example. Let's try to find a lot of these. So I'll do an example with 9. Okay. So n equal to 9. And what I'm going to do is I'm going to put 3 of them in a small equilateral triangle over here. And now if I put the other charges very far away, I'm not going to disturb very much this picture there because they are going to be very far away. So what I'll do is that I put the other ones in a very far away equilateral triangle over here, and some other ones in a very far away equilateral triangle over there. Okay? So then I'll have 4 here, I have 4 there, I have 4 there, and I have 4 over here because these look like the same charge in this big equilateral triangle. So in total, the number of electrostatic points in this case is 12. Okay. And then a question that Maxwell asks in his book, 3 Tries on Electricity and Magnetism, is... Sorry? Oh, 16. I'm sorry. I was thinking about something else. Of course, I have 16. Yeah. Yes, there are. It's really 12 plus 4 in a way. That's why I wrote 12 because I was, yeah, of course. Thank you. So if I split this 4 into 3 plus 1, then that 12 is going to be, that 16 is going to be 12 plus 4. Okay, so and then the question that Maxwell asks is, given n, the number of electric charges, what is the maximum number of electrostatic points that you can have? So that's a question by Maxwell in 1873. Given n, given n, what is the maximum number of electrostatic points? And you can also ask which configurations achieve that. Okay, so that's a question that you can ask, and they conjecture, so Maxwell and J.J. Thomson, that the answer is n-1 square. Okay, so that's correct. In this case, we have 3, n-1 is 2, 2 squared is equal to 4. And you can actually prove that this is the best you can do. But then already on the other case where I had 9, 8 squared is 64. That's quite far from 16. And I don't know how to do better with 9 points, but maybe it's possible. That's right. That's right. You can try to use the third dimension to increase the number of points. I don't know any configuration already with 9 points, even in using the third dimension that does better. If you try to construct with a lot of points, then there is the best way I know to do things uses the third dimension. But one thing that you can try to do if you are trying to construct a lot of critical points is pick that example with the 9 points. You do it like this, and now you iterate this procedure. So you put one here, you put another one here, another one here. You see what I'm doing? I'm iterating this procedure. You get something that grows linearly with n, with a coefficient that is greater than 1. That's important. But you can do slightly better by increasing with the third dimension and doing something similar in one more dimension. But I did a computation some days ago, and I think it also grows linearly with n. Just the coefficient gets better, gets bigger. So I don't quite understand what they had in mind. I read the argument in the book. Apparently, the argument was written by Maxwell first and uses some version of Morse theory, even though Morse theory did not exist at the time. And then when Thomson was revising the book, he wrote more. And I do not understand anything of sports. I mean, I understand everything, but it doesn't clarify the situation. It's not. He was trying to justify this better than what Maxwell did. But Morse theory will only give you a lower bound, at least to my understanding. So I'll tell you now what Morse theory gives you, actually. So what you can do is to first perturb for the generic location of the first charge, phi, the electric potential is a Morse function. So for the generic P1, phi is Morse. And then you can use Morse theory to try to get a lower bound. And you get a lower bound that goes linearly with n. I'll show you how. So these are the points, P1, P2, Pn. The electric potential goes like that. Here, you know, right? And it goes to that constant m at infinity. So this is a picture of R3. This is R3, this is infinity. It converges to m infinity, the constant that I added up to it. It's positive. Let's suppose m is positive. So the picture. And this is phi. And now what I'm going to do is that I'm going to modify phi to define a function on the 3 sphere. And I'm going to define it by adding the value m at infinity. And then I'm going to draw exactly phi, except on small neighborhoods near these points, where I'll add something like that. I'll cut it off. I'll cut the potential there like this. So that's the phi tilde. Is a function on S3. And I do it in a way that's so that I have local maximums near the points P1 up to Pn, but I introduce no other critical points. You can do that. It's not. So let's do that. So if we do that, then this phi tilde looks like phi away from the PIs. Looks like this thing near the PIs. and looks like m at infinity. And it's a function on S3. Okay. So I'll erase up here just to keep this in this board. So I go. And now we do the following. So the other characteristic of S3 is 0, of course. And that's the alternating sum of the number of index I critical points of this function. So this function, so this is the number of critical points with index 1, 0, 2, 3. Index 0 is the minimums. There is only one minimum, which is this one at infinity. So that's 1. Now, nu3 is the number of local maximums. Because phi is harmonic, it will have no local maximums. So if I tilde, the only local maximums it has are these ones that I put here. And that's n, there are n of those. So you get 1 minus nu1 plus nu2 minus n. So we get that nu2 minus nu1 is equal to n minus 1. And so you get at least n minus 1 critical points. That's what this gives you. Okay, so the number of electrostatic points is greater or equal than n minus 1. Okay, so that's what Morse theory gives you. And maybe I'll leave this problem in electrostatics here, and I'll go now to geometry. Are there any questions before I do that?
So if Maxwell and Thomson cared about dimensions higher than 3, you could do this argument on any Rn. Let me not call it Rn, Rk, and you would, it would still be this. Would it be the same? What happens if you do this?
Well, if you use an odd an even dimensional, you get a 2 here, and so. But you could do the same argument. And actually, in R2 is actually easy to tell what the answer is, because in R2, if you use the potential for the potential, the Green's function of the Laplacian, you get the logarithm, right? And then when you take the derivative, you get the real part of an harmonic function of. So you can complete it to an holomorphic function. So actually meromorphic from P1 to P1. And the number of charges is the degree of that function. So you actually know it has degree n. So it needs to have at most n zeros. So in 2 dimensions, this problem is easy to solve. In dimensions higher than 2 is difficult. And it's open. Another interesting question that you can ask is, and what is the minimum? Can you actually find configurations with just the minimum? And I did some experiments, and I'm very convinced now that if you put things in the vertices of a tetrahedron, there is only one critical point at the origin. But I did some other experiments with the other platonic solids. I know that it's for the cube there are more critical points, but on the other ones I'm not so sure, because the computer is not. I've been using Maple, and it's not very good at making the pictures. Anyway, okay, so let's go then to I will call this section Gibbons-Hocking and SATs. So the idea is to describe Ricci flat Kähler metrics. In 4D with circle symmetry. So, and Ricci flat Kähler metrics in 4D, you can also think of these as hyperkähler metrics. And you can regard this construction that I'm going to tell you now as just an explicit way of giving a lot of examples. But in reality, all complete examples with S1 symmetry come from this construction. Okay, so and if you have circle symmetry, then that means that there is a projection from your four-dimensional manifold admitting such a hyperkähler metric or a Ricci flat Kähler metric to the space of orbits. And the space of orbits is R3, or a subset of R3, okay? So this is the projection on the space of orbits. And if you know what an hyperkähler manifold is and what the hyperkähler moment map is, this is the hyperkähler moment map. Okay, so but if you don't just think of this as a projection on the space of orbits. And now, what I promise you is that if I give you some points on R3, like the ones that I had here, P1 up to Pn, points in R3, which you can regard as parameters in the construction of these metrics, and the phi, the electric potential that they generate, that I've also written, then I will reconstruct to you X and with an hyperkähler metric on it, with the Ricci flat Kähler metric. So that's my task now, is to tell you how to do that. Okay. Okay. So in order to do that, what I'm going to do is to describe X away from in the locus where the S1 action acts freely as a circle vibration over an open set in R3. That open set is going to be the complement of these points. Okay, so that's what I'm going to do now. So we want to find a circle bundle over R3 minus those points, and which has curvature the electric field. Basically, that's the idea. So we want a circle bundle X hat. So that's a subset of X over R3 minus those points with a connection theta whose curvature is so F, that's the curvature of eta. In eta, you can think as a one form in the total space, is the Hodge star with respect to the Euclidean metric on R3 of d phi. This is basically the electric field. Okay. So that's the equation. So there are two requirements for this to be the curvature of a connection. The first one is that F must be closed. Okay. So let's check that. So if we take the F, that's d star R3 d phi, and that's basically the Hodge star of the Laplacian. The Hodge star on R3 of the Laplacian of phi. And now the Laplacian of phi, this thing is 2 pi times the sum from I equal 1 to n of the delta pi. This is basically the definition of how you get the electric potential. This is with unit point charges at the points pi. Okay, so that's what you have. And of course, this is 0 on R3 minus the point, because that's supported on the points. So we are good. So this is indeed a closed two form on R3 minus those points. And now we need to check that the homology class that it defines as integral periods around the generators of the second homology of this space. So now we need the second requirement. Sorry, I want to keep this board. I shouldn't have done this, but so the second requirement is that, so second is that if we divide by 2 pi and we look at F, so that's a class in the second cohomology of R3 minus this point with coefficients in R a priority, and we need, so we need instead of R, need Z. Okay, in order for this to be the curvature of a connection on a circle bundle. So let's check let's check if that is the case. So we have P1, P2, up to Pn. So these are points in R3. So the complement of these points, its second homology, is generated by spheres around these points. Okay? And these spheres, they are the boundary of three-dimensional balls around the points. Right? So I need to integrate 1 over 2 pi f around the boundary of these balls or around this point. And by Stokes' theorem, that's 1 over 2 pi, the integral over the small balls around these points of df. But what is df? Sorry, I'll have to go again here. So df, we computed it here, was the Laplacian of phi, and that's 2 pi times the sum of deltas, right? So df, remember, this is 2 pi. This was a pi, I'll call it pj. 2 pi, the sum from I equal 1 up to n of the delta pi's. So basically, this will just give 0 anytime j is different from I, and will give you 1 when j is equal to I. So you get 1. And of course, 1 is an integer. Okay? So there exists indeed this circle bundle x hat over R3 minus these points, and it has a connection eta with curvature that satisfies this equation. Okay, so this exists. So there exists that bundle.
So you can obviously change these unit charges to perhaps some other integral charge.
Then you get an orbifold.
Okay. And what about if they have to be positive? Do they do negative?
I think they have to be positive. Yes, yeah. I think the local, if you want to write locally the metric, you will see that you need the charge to be 1 for the metric to be smooth when you change coordinates, to have to be the radially extended op fibration. And when you have degree higher than 1, what you can do is that the link is no longer the 3 sphere, is the 3 sphere divided by zk, and then so they need to be positive. Okay, so and then you get an orbifold. So we have this thing over R3 minus these points. Okay, so and I'm going to write a metric there. G is going to be phi to the minus 1 times eta squared. Remember, eta is this connection 1 form on the total space, plus this is phi to the minus 1, plus phi times the pullback from R3 of the Euclidean metric in R3. Okay, so that's, so we have, the picture is we have R3 here. With the points P1, P2, Pn, P3. And we have now our x hat over here, which is inside x. And so above every point away from this, above we have a circle. So this is a circle fibration away from those points. And what happens locally at those points? So we can look at the length of these circles. So let me look at the length of a circle, pi minus 1. So this is pi, right? Pi minus 1 of x. That's the integral over pi minus 1 of x of the unit 1 form in the direction of pi minus 1 of x, which is phi to the minus 1 half times zeta. And because zeta is a connection one form, when you integrate it, you get 2 pi. That's the length of the circle. You get 2 pi, phi to the minus 1 half. And remember, phi explodes at these points. It has singularities there. So phi to the minus 1 half goes to 0 at these points. And the computation that I was telling Spiro is that, in fact, if you do a local computation, you can actually complete this space x hat to x by adding points above these points, above the P1 up to Pn. So, for example, if you pick a curve that starts and ends at these points, above it, you get a two-sphere. Okay? And you can take another curve here, you get another two-sphere there that touches this one at that point, which is the preimage of P2, and so on. And you get here, so let's, if this is Pn minus 1, and if this is Pn, take another sphere there. So the space X that you have, that you obtain above, has as many spheres as one less than the number of points that you pick. Okay, so in between, if you only had 2 points, you had a sphere, right? No. So there are as many spheres as these. Okay, so it's and they all intersect each other. This is what is called an AN chain of spheres. Of course, you can take a path like that and you get another sphere. But I mean, in homology, it will be generated by these ones. If you pick an ordering of the points and you take lines connecting the points. So in reality, this X that you have is actually diffeomorphic to a resolution of C2 mod ZK. So this is a diffeo. Okay, it's always diffeomorphic to a resolution of C2 mod ZK. So you get this K minus 1 spheres coming up. Okay, so and now let's ask the question. Let's try and find some closed geodesics here. What is it that you can do? Well, you can try to solve the geodesic equation, but I'm going to be very simplistic, and what I'm going to do is look for fibers, circle fibers, which are closed geodesics. Okay, so let's do that. So if we look at, so we need to look at the length. So geodesics, they minimize, sorry, they are critical points of the length functional, right? So they are critical points of the length. So I'm going to restrict the length functional to the fibers of this fibration. So I get a function from R3 to 0 plus infinity, which picks a point and gives me the length of pi minus 1 of x, the circle above, or maybe it's 0 because maybe it's a point that I pick, right? And we have already computed this. It was there, and it was 2 pi times phi to the minus 1 half. So that's 2 pi to the 2 pi phi to the minus 1 half. And so we arrived at the conclusion that pi minus 1 of x is a closed geodesic. Is a geodesic, of course, it's closed, right? It's a geodesic. If and only if x is a critical point of this function. Oh, at x. And only if x, and the critical point of phi to the minus 1 half is the same as the critical point of phi, which is the same as an electrostatic point. If and only if x is an electrostatic point. So that's where the connection with the electrostatic points comes from. Okay, so and now you can ask several questions about these geodesics. The first obvious one that you can ask is, what is their index? So as critical points of the length. And it turns out that if m, this constant that I added, is very big, the constant that I added in the potential. This is the case that I will be interested on, but also you need it to do the computation. Then the index of pi minus 1 of x as a geodesic. So these are the number of ways you have to deform the geodesic in order to minimize the length. It's 3 minus the index of phi at x, okay? This comes basically because instead of looking at phi, you're looking at phi to minus 1/2. So you get 3 minus that. So in this picture that I have here, these 3 points give me one of these metrics which is hyperkähler in 4 dimensions, is a Ricci flat Kähler metric in 4 dimensions, and it has 4 geodesic circle fibers, and the ones in blue have index 1, and the ones in red have index 1, and the one in blue has index 2. So the number of index 1 is equal to 3, and the number of geodesics of index 2 is equal to 1 in this case. Okay. Okay. So I've told you how to construct geodesics in these hyperkähler manifolds that are non-compact and that have this circle symmetry. But how do you go about to construct them in the K3 surface? So the reason is that there is this construction of metrics on the K3 surface due to Lorenzo Foscolo. And the idea is to look at ways that metrics, Ricci flat Kähler metrics, can degenerate, and they can collapse. And when they collapse to something that is 3-dimensional, so 1 dimension less, so you have something 4-dimensional collapsing, suppose it collapses to something 3-dimensional, then you can use these metrics that I've described to you here to approximate the Ricci flat Kähler metrics on the K3 surface. And then you can grab these geodesics that now exist in the building blocks of this construction and deform them to geodesics on the K3 surface. Okay, so that's the idea. So let me just describe naively how it goes, this construction of the K3 surface in this way. Okay. Sure. That's right. That's a good question. It's so many times when you have a Lie group acting on a functional, and you restrict the functional to the invariants, the fixed set by that Lie group action, the critical points of that functional restricted to the fixed locus of the group action are actually critical points of the whole functional. This is called the Palais criticality principle, and it works in this setting. So, but you need to use the symmetry in order to justify that. In the case of minimal surfaces, this works always. I think that's the theorem of Siang and Lausanne to verify that the Palais principle of symmetric criticality holds in the case of minimal surfaces. But yes, it's a good point. I was brushing over it. But it's okay, very well. So I will now go and describe Foscolo's K3 surfaces. So as I said, you have something that is 4-dimensional, and they can be equipped with a lot of parameters because they describe an open set in the moduli space of Ricci flat Kähler metrics on the K3 surface. But one of those parameters is the collapsing parameter. I'll call it epsilon. And as epsilon goes to 0, the Gromov-Hausdorff limit of this is the quotient of a 3 torus by Z2. Okay, so it's something 3-dimensional. How does that look like? I'll make a picture of the 3 torus quotiented out by Z2. So something like this. Maybe, yeah. Okay, so imagine it's this stuff without the straight lines. So that's a quotient of the 3 torus by Z2. There are these 8 fixed points of the action. So let's call it Q1, Q2 up to Q8. So this is the collapsing in codimension 1. And it turns out that in this situation, the curvature concentrates at points. The curvature concentrates at points. And these points are precisely these points, Q1 up to Q8. And some extra points, P1 up to Pn, that you can pick at will as parameters in the construction. But they are somewhere inside. I'll draw them in a color with colors for us to distinguish. So these ones you can pick yourself, P1, P2, up to Pn. Okay.
This is one possible degeneration.
Yes, you can have them collapse in codimension 2, in codimension 3, also. Codimension 1, I think it's a theorem now that it always looks like this. I think maybe proven by Song and Huobing Zhang, I think. But I may be wrong about that. Anyway, I've said it now. But I think it is a theorem now that if it's in codimension 1, the limit needs to be this, need to be a 3 torus. I mean, of course, it depends on the lattice that you pick. Doesn't have to be the standard one. Okay, so and now this X epsilon, you can decompose it into the region away from the curvature concentration, which is a big region, K epsilon. Basically, you can think of it as this K epsilon, you can think of it as basically a circle vibration away from these points. Okay, where the size of the circles is epsilon. So they are collapsing to these 3 torus, minus the points in that region, the K epsilon. And then there are some small bubbles that appear at these points that you need to glue in at these points. So some bubbles like that, and then some red bubbles. Okay, so union with the white bubbles. Union with the red bubbles. And so this has the property that in K epsilon, the metric is well approximated by the Gibbons-Hawking ansatz that I described to you, but using now the electric potential on the 3 torus, okay, not on R3, on the 3 torus. But of course, you need to have some negative charges somewhere, because in a compact manifold, you need to have as many positive charges as negative charges. So you have -4 charges at the PIs, at the points, at the QJs, so the fixed points, and Ki charges at the PIs. Okay, and of course, because you need the total charge to be 0, that amounts to saying that if you sum from I equal 1 up to n, the QIs, you need to get 16. Okay. Okay, so try not to think too much about it. The reason is that you need to work on the 3 torus, not on the 3 torus quotient by Z2. And then each of these points appears twice, and then the charge on the Q's is really -4. So you have 4 times 8, that's 32, times 2 is equal to 2 times the sums of the KIs. Okay, or if you want to work downstairs, imagine that when you quotient by Z2, actually the charge is not -4, but it's -2. Maybe you could think that way. But anyway, so that's how it goes. And now the epsilon to the -2 times the m epsilon j, this converges to a certain hyperkähler manifold in dimension 4 that is non-compact, called the Atiyah-Hitchin manifold. But I'll just call it AH. I'll not mention it again. I'm just telling you what it is. But if you have never seen it, just forget some guy that we will not see again. And then epsilon to the -2 times the m epsilon I. This is the important one. This will converge to a construction given by the Gibbons-Hocking and Satz. So I'll say here, this guy converges to the Gibbons-Hocking, a metric constructed using the Gibbons-Hocking and Satz, using phi generated, so the electric potential generated by KI charges. KI charges at some points that you pick. So sorry, maybe I'll call it unit charges at KI points. At I'll call it PI1, the I index, the bubble, and PI KI. Okay, so they're not these ones. These are all in here. All in here. This guy, for example, this red guy, it will eventually converge to something that you obtain over R3, constructing by given Pn1 up to Pnkn. And Kn is the charge at this point in the construction of K epsilon. Okay. So, but now that I told you how this goes, the point is that you can use, I know, so based on what we've seen before, we know how to find geodesics here. We know how to find geodesics here. And we, on the Gibbons-Hocking approximation, and then we deform them to geodesics on the whole thing. Here is quite easy to do that. You can use a theorem of Bryan-White to do it. Here you need to do a separate analysis, but it's also not very complicated. But the upshot is that you get some result. I'll tell you now, of course, the result depends very much on which configurations you pick. And I can write to you now a result that you can state in general for any configurations of points. But if you give me a specific configuration of points, then maybe I can do better than the results that I'm telling you. Okay. Because you can investigate it hands-on. Okay. Is there any questions so far, by the way?
The KIs are all, they're not all, they are positive. KIs are positive.
The KIs are all positive. That's right. I'm sorry. I should have said.
So you can imagine that, you have lots of choices, right? Because you have lots of different K3 metrics, different Ritchie plot data metrics on K3. But at least the ones that degenerate this way, it looks like you can almost get an estimate on independent of because there's this constraint that the KI is 716.
Yes.
You can say something about any Ritchie plot as long as it's generating in this way.
Yes. I'll state that now as a theorem. So there is something you can state in general, but my point is that on specific examples, you can do something much better, and you can actually write down explicitly these functions and approximate things in a very explicit manner. So I'll state now a result that one can prove in general. So theorem. So it goes as follows. So let P1 be generic. So I need that to get these more theoretic lower bounds. So P1 is the first point, the first of the red points, one of them. Then there exists at least n+1 closed geodesics of index 1 in K epsilon and 5 closed geodesics of index 2 also in K epsilon. N is the number of charges you pick, the number of points, extra points you pick where the curvature is concentrating when you take the limit of these K3 surfaces.
At most 16, right?
N is at most 16. Yeah. You can choose them arbitrarily. Yes. So that's in K epsilon. So what else can we do in these regions, in the Ni epsilons? So now for I equal 1 up to N, let Pi1, so the first points on the picture is like this first point, be generic. Oh, actually, let me say something else that you can say here. You can actually, because I said locating in the title, right? So these are within, in the Hausdorff distance, around epsilon to the 13/10 of the circles above electrostatic points for the potential you use here. So let's call this potential here phi epsilon or phi epsilon. So you can locate them with this precision. Okay, so now let's go to for I equal 1 up to N. There exists at least N-1 closed geodesics. This is using the bounds that I showed you, using that Morse theoretic argument on the 3-sphere. For this bound here, you need to do a similar Morse theoretic argument on the torus, basically. Exists at least N-1 closed geodesics of index 1 on N epsilon I, and there is a similar precision that with which you can compute them. Okay, so but that's the general result you can prove. So this is what you can do in general. And so maybe to end, I'll give you a specific example that is not in general, where you can do better than the general result. Okay, so. Oh, sorry, here is not N-1, it's Ki-1. So one less than the charge of that bubble. Okay. Before I go on the examples, are there any questions on?
You don't get into index 2.
No, you don't get any index 2 guaranteed. In this case, you get some index 2 guaranteed from the topology of the 3 torus. In this case, because you go to the sphere, it doesn't tell you. But again, in examples, you can find them in this region.
Can the charges be any possible values, or
they need to be integers. That's right, because you need to find these bundles. When I was explaining the construction, you need that the charge to be an integer in order to be able to find a bundle. Yeah.
So the theorem is just your status of explicit example that you use the type of fine right here when you change the method. Yeah?
That's right. Yeah, so there is this result of prime white that tells you that if you have a minimal surface with no Jacobi fields, then you can deform it. So that's what you use in this region. In this region, you need to work separately because the metric is collapsing. is not converging to anything fixed. So you need to do the estimates separately. But it also works out and is not complicated. It's very simple analysis. Sorry? Oh, I don't know the answer to the conjecture. Sorry, it's an open problem. I don't know the. I'll tell you now an example where we can construct a lot of geodesics, but I don't know in general the solution to that.
Sorry, go back to that previous comment. You said that Maxwell and Thompson had some argument for their conjecture, which is an upper bound, right?
Yes.
Using more theory, you showed us use more theory to get lower.
Yeah, that's what I think most theory gives, always lower
Yeah,
bounds.
so did you understand what Maxwell was saying at all?
No, I understand part of what Maxwell says. It seems to me most theory. He's saying, oh, in the places where the potential goes to infinity, we take he says, doesn't call it negative gradient flow, but he calls the cycle that you get by doing negative gradient flow. And then he also considers negative charges possibly. So then he takes the other cycles and then when they intersect and so on.
Get it wrong.
I don't know if he got it wrong. I think the argument, I think there is no argument using Morse theory because he then combines this with other stuff. And then when Thomson wrote more, Thomson also he uses some language that is not. He argues, I don't know if even if he may use the word condensator somewhere. So I don't know. I know what a condensator is, but I don't see how it fits here. Anyway, so let's do this example. So now I'm gonna draw the three torus just like that. I'm gonna lie. And so we have Q1 and we have Q8 there. And then we have, I'm going to choose 4 points. That's P1 up to P4. And so we have these bubbles here. Okay. And I'm going to choose, so these are the bubbles. K1 equal to 1. K2 equal to 3, K3 also equal to 3, and K4 equal to 9. Okay, so these add up to 16. So we are good. There are also these bubbles here given by the Hitchin manifold. And so let's count how many we get. So according to this theorem, I'll get these estimates on the K epsilon region. So that's everywhere where you don't see a bubble. So according to the theorem, we have, because n is equal to 4, we have 5 of index 1 and 5 of index 2. And this is in the K epsilon region. Then on these regions, here, I have only one charge. And within one charge, I cannot produce any geodesics. But with 3 charges, you can arrange them in an equilateral triangle as I did in the example. Okay? And then we add, And then we add these 3 points, which gave rise to geodesics of index 1, and the blue point that gave rise to geodesics of index 2. So on n epsilon 2 and n epsilon 3, we get 6, which is 2 times 3 of index 1, and we get 2 of index 2, 1 in each. Okay, and then we take the guy with 9, and the guy with 9 we will use this configuration, if you remember from the beginning. And in this configuration we had so n epsilon 4, we had 12 of index 1 because it's 4 times this guy, and we had a 4 of index 2. Okay, so in the end, what do we get? We get this plus this plus this. So 23 of index 1. Thank you. And we get 6 plus 5, 11 of index 2. Okay. Okay, so 23 is interesting because it's bigger than 22, and you actually know where they are because it's just near these critical points. And 22 is what you get from doing Morse theory on the free loop space for the length function. So you do better than the Morse theory in this case. And you also can locate them. So that's the Morse theory doesn't tell you anything of where they are. Anyway, that's what I had prepared. Thank you for your attention.